I'd like to invite up Major David Niblick. He is an AI evaluator at ATEC, the Army Test and Evaluation Command. He has served as an instructor in electrical engineering and computer science at the Military Academy at West Point. He's done operations research, systems analysis, and today he's going to be talking about development T&E of small-scale AI models. So I think that's where we're going to see a lot of this stuff in the near term. So, throw it to you.
Thank you. Make sure I have my notes ready. Never want to start without that. All right, good morning. So I am David Niblick. I work at Army Test and Evaluation Command, and today I want to share our lessons learned as we had a project in which we developed a small-scale AI solution to one of the problems facing ATEC. And then we flip that on its side, and given that we are a part of ATEC and it's our job to test and evaluate, the lessons we learned when we treated it like a program of record, tested, evaluated it, and some of the things that we could then extrapolate to other systems of record. I am a teacher at heart, so I like this to be a conversation as much as possible. I'm going to cover things at a high level. We only have 30 minutes to do this, but I prefer if the feedback, if you want to drive this in a certain direction or deep dive into particular areas, I would very much appreciate that. In fact, I see we have some cadets in the room here, so consider it a mandatory task that you must ask me a question. If you don't, I swear I'll call your professors. I'll even call General Reeves right now if I have to. You always want to start a briefing with aggression to the audience, right? That's a good way to approach this. So again, I work at ATEC. I'm part of the AI team at ATEC. We are a fairly new team. I think in the last 3-ish years, 4 years is when this is developed. If I'm wrong, my boss will let me know and put that in my evaluation next. It's our charge to go across ATEC and first find ways that we can use AI to make ATEC more efficient and more capable. But it's also our charge to go out and find ways to properly test and evaluate AI, because that is the big problem facing the DoD and across society as a whole, arguably. So we said, well, we know ATEC is a massive storehouse for data, right? Brian Kelly over there, I'm sure, will agree personally how much data is found at ATEC and how much opportunity, how much low-hanging fruit there is for us to develop AI solutions at the edge, I would say. A lot of potential out there. So if we're developing those solutions, why not use our expertise to properly test and evaluate that, right? Why not kill 2 birds with 1 stone? So what was the problem we found out there? Well, I mean, there are many problems we did, but we decided to really sink our teeth into this particular one. One of our test centers uses a system in which they have a series of sensors, acoustic sensors, out in a large field. We're talking on the scale of hundreds of meters, to identify and multilaterate the location of explosions. So if they're testing munitions in this field, you want to accurately describe where that explosion occurred. And so they have this series of sensors that do that. It isn't trivial, though, to go through the sound waves of those, the data they capture to identify the exact moment of explosion. Obviously, you need to be accurate not only in avoiding false positives and false negatives, but you need to be accurate in the timing of when that explosion occurred if you want to use that data and those time differences between the sensors to multilaterate back to the location of the explosion. In this particular case, I'm going to be somewhat vague here, but we'll say that they needed about 10 meters of accuracy to accomplish this, sufficient for their needs and their testing. So we saw this as an ideal case because this group had a large set of data from previous tests they've done where they went through and they labeled laboriously, to meet their needs. So you have labeled data. We know of, models we could apply to it. We have a great problem to do. However, as always, I'm sure you've all experienced, once you get to the real world problem of it, once you really dig into the data, things are never as easy as they might seem on the surface. We ran into some problems within the data. The last briefer talked about validating your data, making sure it's accurate to the real world. Well, we ran into some issues there. We found, for example, one of the problems was these engineers, they were labeling the data, they were labeling the times of explosions across these sensors in a way that fit their needs, but because of the proprietary software they were using, they had to go back and kind of smudge the actual labels in order to minimize the residual error at the end of the multilateration process. And so the data that we got, the labels we got, you would expect some consistency in where these labels occurred in the waveform. Maybe they're always at the peak, or maybe they're always at the first rise, where you want to have consistency. But we found that that was not the case at all. The labels were kind of all over the place. So first big problem we ran into. Another problem, we realized it was a bad assumption to think that the order of explosions would be consistent across the sensors. In our minds, we expected the first explosion in sensor 1 would correlate to the first explosion, sensor 2, and so forth. What we found was that was not at all the case. Due to the way that they tested, some of these explosive events occurred in very short proximity in time. And also, given that we're talking hundreds of meters across this field, depending on where the explosions occurred, you might have some flipping across the sensors of where that was. So it was an interesting problem to face within the data, as well as some other ones here. So getting into the development of the solution itself and the lessons we learned along the way. We broke this into two problems. First problem was detecting the explosions and making sure that they were localized as accurately as possible. Second problem, matching those detections across the sensors. Now for audience participation, which of those two problems do you think ended up being more difficult? If you think it was the detection side, go ahead and raise your hand right now. If you think it was the matching side, raise your hand. All right, good. For those remotely, the matching side won out heavily, which means you all are correct. You all get A's for today. Congratulations. So starting, though, with the detection algorithm, we, being the AI team, wanted to jump right into building neural networks for this problem because why not? That's the fun stuff, right? We're an AI team. Let's do AI. So we have our labeled data. We did after our data exploration, some first easy, minimal viable experiments, which first lesson, make sure you do your experiments first, explore that data, try to reduce the assumptions you have with experimentation. We finally dug into developing our actual algorithm. We built some neural networks, and we found that even with small neural networks, they were pretty slow. The idea was we'll have a network. It would essentially convolve across each sensor, across the timestamps, and identify, is there an explosion here? And if there is, then we do some post-processing to try to localize that explosion as accurately as possible. But it ended up being much slower than we realized. One of our constraints was we wanted to make sure that this could work on a laptop such as this one right here. So doing neural network on a CPU of a laptop isn't the best thing. But because of the users we were building this tool for, this is basically what they had to work with. Eventually, that's not going to be the case, but for the short term, this is what we're working with. So we decided we're conducting some signal analysis, right? Let's use those signal analysis tools to help focus in our networks. We moved over to the frequency domain, built some spectrograms, used the data we could gather there to help focus in what our networks were doing. It sped up the process, which was good, but our accuracy was still not where we needed it to be. We kept running into this would work in the ideal case, but the moment that we had any complexity in our problem set, our algorithms were not working the way we needed to. And by complexity, I mean explosions that were occurring close in time, explosions that were occurring when there was some high atmosphere conditions like wind speed, stuff like that. It was causing issues for us. So we changed up our dynamic here. Instead of building neural networks, let's go back to the more classic methods. I joke that were we undergrads at the time we were doing this, we probably would have started by using some Python libraries that already existed and started with just finding peaks and working off of that. And we probably would have saved ourselves a lot of time and been out to drinks that night, after turning in this assignment really quickly. So, but that was not the case for this one. But I think the big lesson learned is start simple first and then build up. So we worked with a peak finder library. We started adding some filters to it, and then we realized we have essentially feature engineering building blocks that we're working with. So instead of us trying to hand jam these and iterate on our own slow human, fingers, let's build a genetic algorithm to help find the right combination of feature engineering to solve this problem for us. And that ended up giving us the best object detector, the best explosion detector side, and we were finally getting the level of accuracy that we needed for detecting the explosions. However, we moved on to the matching problem. Now, in reality, these were both happening in parallel. We didn't just do one and then move to the other because they work hand in hand. But this ended up being the significantly tougher of the two problems. We started off with treating this like a literal matching problem, an integer matching problem, which we had a matrix that correlated to explosions and the different sensors, and we essentially tried to correlate those explosions across the sensors as best we could. That ended up being a very brittle solution, though. Any false positives, any false negatives, even when you tried to handle them with some heuristics and some masking, we couldn't get it to be robust against the complex issues that we were coming across. So then we thought, well, if the goal is to minimize the residual error you get after doing the linear algebra problem of multilateration, why not build a non-linear optimizer that just minimizes the residual error, that being, our objective function, by changing the inputs of how we matched up our explosions across the sensors. And we started to have a lot of success there in matching the problem. There's a couple different, methods we tried. We can deep dive into those if you want to, but the outcome was we were able to optimize this problem. We were able to start matching appropriately. It just took a long time because nonlinear optimization, as you can imagine, can take a while. And when you're doing that again on a laptop, it just wasn't as feasible as we wanted it to be. So we tried to improve upon that. And we moved to what we called a direct generation problem, in which we broke our field out into a grid, both in 4 dimensions, essentially, grid not just in space, but in time as well. And we took the idea of, if you imagine in 2 dimensions and you're trying to multilaterate a location, if you start with the location itself and you take the 4 corners of that box, and then knowing the speed of time and knowing the location of your sensors, you could backtrack and find the left and right limits within the sensor's timestamp of where you could multilaterate from that back into the box. So essentially working backwards, we thought, well, let's recursively create this grid and then search within that grid and making smaller and smaller grids until we found, work backwards, eliminate detections that couldn't possibly have fit within that grid. And by doing that, we found a much quicker, faster way to localize where those explosions occurred and matching them across the sensors. And again, there's a couple different ways that we ended up doing that. But we finally had a detection algorithm that worked, a matching algorithm that worked. We're getting the results we needed. We had a solution that met our 10-meter accuracy. For the most part, though. So now flipping this problem over into the testing and evaluation world, we found that even in a very controlled environment like this, it was one field we were working with. We didn't have to operate this when the weather was really bad. We had a lot of control over this. But that said, working with algorithms like we found that the environment and the operational conditions had a massive impact on our success. It's unavoidable. So one of the lessons we learned from the testing side was you need to view everything through the lens of your environment and your conditions. Starting with the requirements, if 10 meters of accuracy was our requirements, well, when you view that through your environment, does that mean you have to be that accurate across all weather conditions, across different munition types, for example? What are those variables that are critical, and how can you apply that? Because eventually, after you do this testing loop and you're going to communicate your results to the user, to thinking now outside of this particular problem, but to some commander that will be using this, you want to be able to speak not just in a pass-fail method. Right now, ATEC does a lot of their evaluations, and they kind of try to summarize it into a pass-fail mentality. But I argue we need to get away with that. We need to talk more in capabilities and limitations of a system, and then we need to inform those capabilities and limitations by the risk associated with it, risk associated with environment and conditions. In the Army, when we field a system, we want to try to make that system something that we can use anywhere in the world. But I think we can all appreciate the fact that when we're getting into AI-enabled systems, we might need to step away from that and start thinking, well, what environments are these systems validated for? And if we move away from those environments, how can we quantify the risk that is associated with that? So that's, again, even in this very tightly controlled environment, that's what we started to find. You can't control everything, especially when you get away from something that is just a multilateration system working on one single field out there. That becomes an even bigger issue. So that was, I argue, our biggest takeaway when we try to think of the grander challenge of testing and evaluating AI. And by the way, I acknowledge this is not a full encompassing model for testing and evaluating AI. This is just kind of one lesson we learned from it and an approach that we gleaned from it. Of course, another side, and this is covered in much of the literature out there, we need to make sure that our testing loop is as fast as possible. Ideally, it's automated as much as it can be, and it has to be focused on the data itself. As a tester, if you aren't as familiar with the data that is in your operational space that you're using to test, then you are failing. Development, of course, you have to be knowledgeable on the data, but when you're testing, you'll have to be equally knowledgeable on that data. And if we are testing and we aren't aware of the data, I understand that at ATEC we're not always going to have access to the data used to train a model, which is a big problem. But even if you can't use that data, you have to be very knowledgeable on the data that you do have available to test and train your model. And again, if you all want to, we can come back to this and pull a thread on this more. But I'll show the example of how we applied that to this particular problem. So when we had our final output of our development stage, we ran through the battery of tests. We realized on average our error was pretty awful. As you can see, 121 meters of accuracy is far from what we needed. However, when we looked at the median error, we were almost right on at 10 meters of accuracy. Again, accuracy of where we estimate the explosion occurred versus where it actually ended up being. Now, anytime you have a difference of your mean and your median, that usually means you have massive outliers pulling it out there, right? And so looking into now the lens of environment and operational conditions, we thought, well, how can we pull this apart and figure out really what is going on here? So we looked at the impact scattering, i.e. how close were these explosions occurring in time and in space. We were able to realize our current model actually handled that very well. That was not really increasing the risk of failure that much. Speed of sound and other atmospheric effects also were not really messing us up that much either, which was great because those, at the beginning of our development, those were kind of the boogeymen, if you will. Those were causing all the errors. However, one of the operational conditions that we needed to operate with was air explosions versus ground explosions. And we found that with air explosions, this was a big limitation of our model. We could not handle air explosions. And that kind of makes sense because, again, if you can imagine, these are sensors surrounding, a large field, but they're all roughly the same height. They're all probably 10, 20 meters up there on these poles to do that. So that's great for the lateral detection, but as you're starting to get this height advantage, there's not a lot of ability for those sensors to find the discrepancy there. So one of the takeaways that we recommended, if they want to improve their system, vary the height of their sensors as well as the lateral location of the sensors. But right now our model wasn't built on the ideal case, it was built on what existed out there, and our model is not able to handle air events that well. The other operational condition we looked into, and these are just a few examples of many, but the other operational condition we looked into was the type of munition and how that affected our capability to localize it. Without going into the specifics of the actual munitions that are being tested, we found that although statistically speaking, the p-value was not less than 0.05, but when looking at this, you could say there's some increased risk at least. There's some when you're using the type Y munitions, you're likely not going to get the same level of effectiveness, same level of performance that you would with type X munitions. So, kind of in general terms, our evaluation would be along the lines of this, the system passes, if you will, but under certain conditions, breaking those conditions out along the idea of environments and conditions. We know that we're good across a lot of the environmental effects within this one location. However, the operational condition of air events, that is a limitation. We fail at that. This model should not be used for that particular thing. If you are changing your munition types, a type X and type Y, we are validated against. There's some increased risk with type Y, but it's all within the bounds that our requirements were given us. However, every time you're going to change that munition, you are probably going to need to revalidate data and run a battery of tests. Again, hopefully a very short test loop, a very automated test loop, but you'll need to test again to get more data to confirm that. So as an example, that is the type of evaluation that you might need to produce. Overall, though, our observations, data understanding is critical to both sides of the coin. Whether you are developing or testing and evaluating, you need to understand that data with the same level of familiarity. We need to not speak and pass-fail, but we need to manage it as a risk mitigation procedure when we're communicating the results of our testing. And it has to be managed through the lens of environment and the operational conditions that this system must operate under. And then again, test loop has to be automated as possible, not only for the sake of the fact that you're going to keep iterating on it, but after we deploy a system, it's been talked many times at this conference and talked many times out in the greater community. AI, if it's going to be a learned system, there needs to be a way that we maintain that AI, right? That's what the keynote speaker said earlier. And you can't maintain it if you need a battery of subject matter experts out there in the field running their laborious tests in and out. So that concludes my high-level discussion of what we did. I would love if you come back now with me where we want to deep dive into this or what sort of questions you might have of this. Yeah, sorry.
Sure, I'll do it.
Bravery right there, by the way, people. Bravery.
Joey here, sir. How do you think, so some of these challenges that you saw in validating the data and the model, how do you think that would scale to a larger model, a more difficult problem? Do you think it would change in entirely new ways or just intensify or something along those lines?
So a lot of what we did, that's a great question. A lot of what we did was very manual. It was us, because it is acoustic data, it's easy to look through visually. We're talking, again, it's a small scale problem, so we're talking megabytes to gigabytes of data. And if we needed, we could play out the data on our speakers. And our ears are great tools for finding imperfections and all that. So we were able, in this case, to go through it manually, find the issues, find ways to fix the issues. At scale, though, you are not going to be able to do that manually. You might be able to sample it with your eyes, but we're going to need a robust set of tools to help us validate our data sets. And we have some tools available to us now, but not enough, frankly. And the tools that we do have available are for certain domains, the widely used domains, RGB sensors, for example, acoustic, different types of tabular data. There's plenty of tools out there to validate that data. But the Army doesn't just use RGB sensors. A lot of the systems that we observe out there are using all sorts of sensors outside of RGB, infrared sensors and all of that. And there are not as many tools out there to help us validate with those more obscure sensors that the Army specializes in, but not the rest of society. So I think that is one of the problems that we're going to need to solve is building those data sets, building tools to validate data sets with the types of sensors that are pretty unique to the military.
Hi.
I'll go with him with the mic, and then I'll bring it up here. Yeah.
I was just wondering if for the air explosions, if you took height out of the error, if your results were improved at all.
That is a great question. We didn't take height out of the air, but part of that is because for the sake of our users, they needed to. When they're conducting those air explosions, height was a big part of the accuracy they needed. So we didn't try that. I'm kind of curious now. I might go back and see what we get if we take height out of it. But at the end of the day, for our users' sake, it wouldn't have worked out anyway. Yep.
So I'm interested in this from the perspective of you, in this experiment, did contractor development operational test. You wore all the hats
Yes,
and had all the information. But in a shifting left sense, you've got lots of information that cover that whole cycle.
Mm-hmm.
But what if you were not wearing all the hats? What are the things you wish you could tell yourself when you were wearing your contractor hat that you only learned in development tests? What's the information that you feel needs to flow backwards out of this or forwards? What is the information that you as doing the operational test needed from the developer that also happened to be you, but you might not have had?
Right. No, that is a great question. I think one of the problems seeing all of the hats almost makes it a little difficult to think, oh, well, if I didn't wear that hat, because I have to kind of step away from it a bit. But I could see on the test side, if we are getting data that is not acceptable for the testing of a system, then we are already hamstrung, and there's only so much we can do. So I think in the contracting side, you have to consider what sort of data will be provided by the vendors, or if not provided by the vendors, how is the testing community going to get access to data to use for testing? And there's a lot of considerations there, such as not only is the label, not only is the data representative of real world conditions, but are the labels accurate and accurate for the purposes that we need them to be accurate for, not just for the purposes that they were labeled to meet the needs of the engineers labeling them, for example, which is what we ran into. But also another thing that we and my team keep thinking and coming back to is security of that data. How are we making sure that that data wasn't used for training to develop the algorithm? And how are we making sure that it is, indeed secure for testing? There's a lot of great data out there, but again, with a lot of these systems, if they're using obscure tools or they're using data and they're fusing the data in ways that is unique to that system, then frankly, that vendor is the only one capable of making the data that can be used to test it. And that is a big problem for it, because if anybody knows, if you have to trust a vendor and say, I'm going to trust you and use that to train your model, and we're going to use it to test, that it's a big problem. So. Okay, yeah.
So I'm curious, kind of trying to use more of your acoustic data. Did you find any utility in any reflections? So not the peak, but the next peak.
Right. Yeah. So there was the only issue with the reflections problem was the fact that some of those reflections could actually be their own unique explosions through a wrench into it. Because again, some of those explosions, some of the munitions might have been purposely exploding in very short order. So it became somewhat difficult to pull apart what were just reflections and what were their own unique explosions. We did some signal processing to help us with that, but that became a difficult problem in and of itself, and making sure that we're able to pull those two apart was. Okay. Here we go. Final question.
I have somewhat of a basic question here, but you said that you went into this with, it was a very laborious task. Mm-hmm. Did you actually save anybody any time?
Yes,
Okay. And then with the going forward, having to revalidate it each time, are you seeing increasing returns, or is it going to be that same little bit of savings each time?
So we did save time. One of the reasons we sunk our teeth into this particular problem was because this is a test that was used all of the time. And so any saving in the process would have a large return on investment. And that was one of our goals when we went across ATEC to find these data sets and these problems, was we wanted, maximize our return on investment. So we did save a lot of that, the engineer's time in really detecting the explosions, because that required going through line by line, and that, as you can imagine, was laborious. This is still pretty new and being used, so we're still getting feedback on how much time it's saving them. We haven't had to try it on a new munition yet, and so we don't really have that practice of, now what is this automated? We do have some automation built into that test loop to give back feedback if they want to use it out there with a new munition and see, will it work or not? I don't have yet how much that will save, and if they'll need to come back to us with a new munition type to see, hey, this tool you gave us isn't quite working the way we wanted. I'm sure there'll be some iteration that'll occur, but overall, yes, this did work. We met our goal of saving those engineers at that center a lot of time. Thank you. Thank you very much. Thank you.